Okay, so it says here that a small sample of the metabolite was isolated and analyzed by combustion analysis. Combustion means react with oxygen. And if it's a hydrocarbon, it'll produce carbon dioxide and water, which in this case it does. It tells us the results showed the compound was made of oxygen, carbon, and hydrogen. And the 10 milligram sample gave 22.44 milligrams of carbon dioxide and 5.49 milligrams of water. And the question is, determine the empirical formula of the metabolite. Right, so to solve this problem, we're going to start off by assuming our compound contains carbon. Let's say it has X number of carbon atoms. Hydrogen, let's say it has Y number of hydrogen atoms. And oxygen, and let's say it has Z number of oxygen atoms. And when we react it with oxygen, when we burn it, when we combust it, it ends up forming carbon dioxide and water. Now, this equation isn't necessarily going to be balanced. Okay, so we have no idea what numbers go there, there, and there. And we're trying to work out the empirical formula of this metabolite. So the first thing we do know is how much carbon dioxide and water, so 22.44 milligrams of carbon dioxide, 5.49 milligrams of water. We know that's how much was produced when we burnt a 10 milligram sample. So we're starting with 10 grams of this, and we don't know the number of moles. This is a mass value, and it's in milligrams. It's best to convert this into grams, so that's easy. 10 times 10 to the minus 3, which is the same as dividing by 1,000. And we know it's producing 22.44 times 10 to the minus 3 grams of carbon dioxide, grams of that one, and 5.49 times 10 to the minus 3 grams of that one. If we know a mass, we can work out the number of moles of carbon dioxide and the number of moles of water that were produced. And if we have a number of moles, we can then start to make assumptions and actual calculations about how many moles of carbon, how many moles of hydrogen, how many moles of oxygen there were in our 10 milligram sample. So that's the starting point to solving this problem. So to work out the number of moles, we need to know the MR values. We obviously don't know the MR of this one, so that's still a question mark. The MR of carbon dioxide is the mass of 1 mole of carbon dioxide, which is just 44 grams. So if I had 1 mole of carbon dioxide, it would weigh 44 grams. I'm going to include units to make sure we can keep track of what the units of whatever we're calculating is. Same goes for the H2O, it's got an MR of 18. So I will write down 18 grams per mole for this one. Now I can work out the number of moles N, because we know from our formula that number of moles equals the mass divided by the MR. So that's what we're going to be using. Now, in a calculator, if you plug this in, you're going to get the following. Okay, so for carbon dioxide, it gives us 5.09 times 10 to the minus 4. And for the water, it gives us 3.05 times 10 to the minus 4 moles. So these are moles. Now that we know the number of moles of these, we can work out how many moles of carbon there must have been in our sample, and we can start to get a clearer picture of what this metabolite actually is, what its empirical formula actually is. So now that we know the number of moles of carbon dioxide and the number of moles of water, we can actually work out the number of moles of just carbon and just hydrogen that must have been in our metabolite, or at least in 10 milligrams, or 10 times 10 to the minus 3 grams of our metabolite. To do that, all we need to know is the MR of just carbon and the MR of the hydrogen in the water. So if I were trying to work this out, I'd again use this formula, but this time I'm trying to find a mass, and mass equals number of moles times by MR. So in this instance, to find the mass of just carbon, it would be 5.09 times 10 to the minus 4 multiplied by the mass of carbon and carbon dioxide. The MR of just carbon and the carbon dioxide is 12. And if I times that by 12, that gives me 6.1 times 10 to the minus 3 grams, or 6.1 milligrams. It might even be easier to keep these in milligrams, or we can keep them in grams. It's up to you how you solve this problem. In the same way, we can do a similar thing to find the actual mass of just hydrogen that must have been in our sample. And so we'd take this number of moles, times it by the MR of hydrogen in our H2O. This time, however, we have to realize that the number of atoms in every molecule of water is 2. So we wouldn't be timesing this by 1, which is the MR of hydrogen. We would actually have to times this by 2. So it's this number times by 2. That gives us 6.1 times 10 to the minus 4. And again, that is in grams. Now to calculate the mass of oxygen that was in our sample, all we'd have to do is to add these two values up, this one and this one, and take them away from the original mass of the sample, which is that one. That will give us the mass of oxygen, because there was nothing else in the sample other than carbon, hydrogen, and oxygen, and that mass must have ended up somewhere after the combustion. So we just simply have to work out the total of these two, subtract them from the 10 times 10 to the minus 3, and would have our mass of oxygen. So to calculate the mass of oxygen, it would simply be the 10 times 10 to the minus 3 grams that we had before, minus 6.1 times 10 to the minus 3 grams of the carbon in the carbon dioxide, minus the 6.1 times 10 to the minus 4 grams of hydrogen. And that would end up giving us the mass of oxygen, which is then 3.29 times 10 to the minus 3 grams, or in milligrams, 3.29 milligrams. Now that we have the masses, we can work out the empirical formula of our substance. And to work out the empirical formula, all we need is our three substances, our three elements, carbon, hydrogen, and oxygen. We need their masses, which we've now got as mass of carbon, 6.1 times 10 to the minus 3, mass of hydrogen, 6.1 times 10 to the minus 4, and our mass of oxygen, 3.29 times 10 to the minus 3. This is a mass. We can work out a number of moles by dividing by the MR of these, so that one divided by 12, that one divided by 1, and that one divided by 16. And then we have a ratio in number of moles for these three elements. The ratio we get is 5.09 times 10 to the minus 4 there. Be exactly the same as that one, because all we've done now is dividing it by 12. For this one, it would be 6.1 times 10 to the minus 4. And for the oxygen, we have to divide it by 16, so it gives us 2.05 times 10 to the minus 4. This simplifies fairly easily, because they're all times 10 to the minus 4, to a ratio of approximately 5 to 6 to 2. From this, we can work out that our empirical formula for CXHYOZ must be C5 H6O2. So the answer to part A was C5H6O2. The answer to part B requires you to find the molecular formula of the substance. So part B tells us that 15 millimoles of the metabolite had a mass of 2.94 grams. We've got a number of moles, and I know it's millimoles. Milli just means 1,000th of. So all we'd have to do is divide this number by 1,000, and we'd have the number of moles. This is a mass. We can use our formula to find the MR. So MR equals mass divided by number of moles, which is going to be 2.94. That's in grams, so this has to be in moles rather than millimoles. 15 divided by 1,000. And that gives us an MR value of 196. So our compound has to have an MR of 196 grams per mole. What we then have to do is find the MR from our empirical formula. And the MR of our substance from our empirical formula would be 5 times 12 added to 1 times 6 added to 16 times 2. And what you'll find is that this gives you exactly half of 196. So if you plug that into a calculator, well, 5 times 12 is 60. 60 plus 16 times 2, so 60 plus 32, ends up giving you... if we work this out, the MR value is 98. So our empirical formula is not the correct molecular formula, because from part B's information, our MR value of our metabolite is actually 196. The relationship between these two values, this 98 and this 196, is that one is half the other. And so all we have to do is times our entire formula by 2 in order for it to have the correct molecular formula. So if we times our formula by 2, it'll now be, instead of C5, C10, instead of H6, it'll be H12, and instead of O2, it's going to be O4. That is our molecular formula of the substance.